So we learned how to do polynomial division. Most importantly, we're going to be using synthetic division to find zeros of polynomials, but we can use other formulas or theorems to help us narrow down our choices when we are trying to find the zeros of the polynomial. Because now that I know how to do synthetic division, I can just test any root, any possible root, potential root, to see if it is actually a root. If I get a remainder of 0, which I can then write the factor. But I'm pulling from an infinite number of possible potential roots because we have an infinite number system. So if we could find ways to narrow down our choices, we can choose wisely what numbers to test and then streamline the process, hopefully make it faster to find the zeros of polynomials. So the first theorem is the remainder theorem, and this one doesn't as much help us narrow down as it does give us information about the well, not necessarily information, I said that wrong, gives us another way to evaluate a function that doesn't involve plugging in and calculating. So what the remainder theorem says, that if I have a polynomial, let's call it f of x, and I know that that polynomial is divided by x minus k, that means x minus k is the factor. The remainder is the function value at k, and this is k, the root. So if the remainder is 0, then it's a factor and the function value is 0 because it divided in evenly. So let's look at an example of that. What this tells me is the function value at k will equal the remainder. So if I had f of x equals x to the 5th plus 4x to the 4th minus 2x cubed minus x squared plus 3x plus 5, and I want to find f of 3, up until now what I would have to do is plug the 3 in and take 3 to the 5th and then 3 to the 4th and multiply it by 4, and then take 3 to the 3rd and multiply it by -2, and then take 3 squared and then 3 times 3 and then 5, and then I would have to combine all of those numbers, and that's a lot of work. But what the remainder theorem says is that if x minus k is the factor, k is the root, if I do synthetic division, x to the 5th, 4x to the 4th, -2x cubed, -1x squared, 3x, and 5, and I do synthetic division, 1 times 3 is 3, 4 plus 3 is 7, 3 times 7 is 21, 21 plus -2 is 19, 3 times 19 is 57, plus -1 gives me 56, 3 times 56 is 150 plus 18, so 168, plus 3 is 171. 171 times 3, already did it on my calculator, 513, and 5 plus 513 is 518. This is my remainder. This is my remainder. The function value is the remainder. If I plug 3 into that function, I will get 518, and I didn't have to take 3 to the 5th, and I didn't have to take 3 to the 4th, and all I had to do was multiply and add. And most of those I could have done in my head, so it doesn't even take a lot of calculator work. The remainder theorem is really nice in that it gives me another way to calculate a function value, but we're also going to see it help us along the way when we are looking at finding zeros of polynomials. I believe that you guys had the rational zeros test last year in Algebra 2. It says that if I have a polynomial defined as such, where I have the leading coefficient, a sub n, just like we've always had, a sub n is my leading coefficient, and a sub 0 is my constant term. And if I have integer coefficients, then the rational zeros will be, in lowest terms, P over Q. P is a factor of the constant term, and Q is a factor of the leading coefficient. So if we want to list the possible rational roots, we need to look at factors of the constant term and factors of the leading coefficient. So my constant term is 6. We don't put the sign on it because we are going to be looking at plus or minus. So the factors of 6 are 1, 2, 3, 1 times 6. So there are 4 factors of 6. And then my factors of my leading coefficient, I don't know why it is weird over there, are 1, 2, 2 times 5, and 1 times 10. So my possible rational zeros or roots, they're called zeros because that's where the function equals 0. So we are looking at our possible rational zeros. So I'm going to take my constant term factors and list them, and we could have positive or negative. So I have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, because those are the factors of 6 divided by the first factor of 10. And then I'm going to do the same thing again, but this time I'm going to divide by 2. So I now have plus or minus 1/2, plus or minus 2/2. 2 divided by 2 is 1. I already have that listed. Plus or minus 3/2, and then plus or minus 6/2. 6 divided by 2 is 3, so I already have that one. Then I need to divide by 5. So then I have plus or minus 1/5, plus or minus 2/5, plus or minus 3/5, and plus or minus 6/5. And then lastly, I am going to divide by 10. So I have plus or minus 1/10. 2/10 is 1/5. I already have that. Plus or minus 3/10. And then 6/10 is 3/5. So I have all of my possible rational zeros, which are 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I have 24 possible rational zeros of this polynomial. Now, it's possible that the polynomial might have irrational zeros, like square root of 2, right? Square root of 3. So we'll learn how to find those later also. But if it has a rational zero, it will be one of these 24, which still seems like a relatively long list. But when we think about the fact that we are going to be not testing from an infinite number, not pulling from an infinite number of possible zeros, it does limit my list quite a bit. So we're going to look at how to use those here in a minute, but I want to also talk about upper and lower bounds theorem. So this again is a way that you can just, you can just limit the number of roots that you need to test. I'm going to move this up a little bit. Give myself a little more room here because I didn't need as much room there. Okay. So what the upper and lower bounds theorem says is that if we have a function, let's call it f of x, and some number k, like we are testing up here, k, we're going to check for k as a possible potential root or zero of the polynomial, and we are using synthetic division, synthetically substituted. That means I'm using synthetic division. What this says is if k is positive and all of the numbers in the result are positive, both of those have to be true, then k is an upper bound. So what an upper bound means is there will be no more zeros above that value. It is a boundary. There are no zeros beyond that value, okay? So if I were to test 6 into some polynomial synthetically, I should write the polynomial. Let's call it f of x is 2x cubed minus 4x squared plus x minus 1. And then let's just test 6 into 2, negative 4, 1, negative 1 using the synthetic division. 2 times 6 is 12. 12 plus negative 4 is 8. 6 times 8 is 48. Plus 1 is 49. 6 times 49 is going to be a much larger positive number than negative 1. And I see that this is now positive. So it says here, if k is positive, 6 is positive, and all the results are positive, both of those are positive, then I can say that 6 is an upper bound of the polynomial. That means there will be no zeros above 6. So if I were looking at this, it doesn't help on there. But if I knew an upper bound, let's say a new upper bound was 2, now anything bigger than 2 I don't have to test. If I know 6 is an upper bound, any possible root bigger than 6 I would not have to test. Now it also says that if k is negative, so if I'm testing a negative number and my results alternate signs, then k is a lower bound. So if I take, let's try negative 2, negative 2 is negative. The number I'm testing has to be negative for it to possibly be a lower bound. That doesn't mean that a positive number can't be a lower bound. It's just that we can't test a positive number for a lower bound. So here if I do 2 times negative 2, I get negative 4. Add them is negative 8. Negative 2 times negative 8 is positive 16. I get positive 17. Negative 2 times 17 is negative 34, plus negative 1 is 35. So what I see here is that negative, I am testing a negative number, and the results alternate signs. Since they alternate signs, I now know negative 2, why is it not working? Negative 2 is a lower bound of f of x. So then I would not have to test any values less than negative 2. This also tells me, using the remainder theorem, I know f of negative 2 is negative 35. So I also know that function value. So let's put all of this into practice, and we want to find all of the roots to this polynomial. So I want factors of my constant term, and then I want factors of my leading coefficient. So I made this one big on purpose. It's going to be not a lot of fun, but so that we can see some of these things in practice. So 1 and 90, 2 and 45, 3 divides into 90 30 times. 5 divides into 90 18 times. Oops, I hope I gave myself enough room. 6 divides into 90 50 times. And 9 divides in 10 times. Didn't quite give myself enough room. And then my factors of 4, that one's easier, 1, 2, and 4. So when I write my possible rational zeros, I am going to have a very long list. Dividing by 1, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5. Your tendency is going to want to be to not write the plus or minus with each term. Avoid that, because when we are looking at upper bounds and lower bounds, we would only be crossing off a sign like -3, not necessarily +3. So we want to be able to see that for each of them. So plus or minus 6, plus or minus 9, plus or minus 10, plus or minus, why did I write 50? I wanted 15. That should be 15. Oh my goodness. Plus or minus 15, plus or minus 18, plus or minus 30, plus or minus 45, plus or minus 90. Just realize this is a larger list than we would normally have. Now let's divide by 2. Plus or minus 1/2. Plus or minus 2 halves reduces to 1, so I already have that one. Plus or minus 3 halves, plus or minus 5 halves. 6 halves is 3, plus or minus 9 halves. 10 halves is 5, plus or minus 15 halves. 18 halves is 9, 30 halves is 15, plus or minus 45 halves, and then 90 halves is 45. I have that. And then let's do the last one, the 4. So I have plus or minus 1/4, plus or minus 3/4. 2/4 is 1/2, which I already have. 3/4 plus or minus 5/4. 6/4 reduces to 3 halves. Plus or minus 9/4. 10/4 is 5 halves. Plus or minus 15/4. 18/4 is 9 halves. I already have it. 30/4 is 15 halves. Plus or minus 45/4. And then I have 90/4 is 45 halves. I have all of them. Yes, this is an incredibly long list. You would not expect to see a list this long on a test, but it is still less than an infinite number of numbers to choose from. So now what we're going to do is we are going to do a condensed version of synthetic division. So we're going to start with our polynomial. So I want 4x to the 4th negative 43 x squared. Oops, I need 0, x cubed, negative 43 x squared, negative 9x, and 90. So we have to make sure all of our degrees are accounted for. So now I'm going to pick a number and just test whether or not it is a 0. So I like to pick a number sort of somewhere in the middle. And if I have an option, I like to take positive versus negative. So I'm just going to try 9. So basically what I'm doing is I'm eliminating that middle row of the synthetic division, and I'm just writing the result. So I'm going to bring down 4. 9 times 4 is 36. 36 plus 0 is 36. 9 times 36 is 324 plus a negative 43 gets me 281. 9 times 281 is going to be a significantly larger positive number than negative 9, and then a really big positive times 9 plus 90 is going to be a really big positive. And what I see here is I found that I have an upper bound. And what I want to do off to the side of my synthetic division is communicate when I find information. That is going to be part of your grade. So here we're going to now cross off any number greater than 9. So positive 10, positive 15, positive 18, positive 30, positive 45, positive 90. 15 halves is 7.5. That's not greater than 9, but 45 halves is 45 fourths is also greater than 9. So I have eliminated 1, 2, 3, 4, 5, 6, 7, 8 from my long list. So now I'm going to go smaller. Let's try 2. So I bring down the 4. 2 times 4 is 8. 8 plus 0 is 8. 2 times 8 is 16. 16 plus negative 43 is negative 27. 2 times negative 27 is negative 54, plus negative 9 is negative 63. 2 times negative 63 is negative 126, plus 90 is negative 36. And then I believe earlier we looked at intermediate value theorem. If we did not, you're going to need to remind me, because intermediate value theorem says that if I have a continuous function and I have a positive function value and the remainder is our function value, and a negative function value, somewhere between there needs to be a 0 or a root. So that means between those two I have a root, and I'm going to claim because of the intermediate value theorem. So let's just try 3. So when I try 3, I have 4. 4 times 3 is 12, plus 0 is 12. 3 times 12 is 36, plus negative 43 is negative 7. 3 times negative 7 is negative 21, plus negative 9 is negative 30. And 3 times negative 30 is negative 90, plus 90 is 0. And I have found a root. And now you are going to stop with the synthetic division, because this is a root. That means x minus 3 is a factor. So I am now going to actually factor my polynomial. I was at x to the 4th. So I now have 4x cubed plus 12x squared minus 7x minus 30. I have now gone from a 5th degree polynomial to now I need to check a 4th degree polynomial to a 3rd degree polynomial. So I also now am not looking for factors of 30. I'm looking for factors, or not factors of 90, but factors of 30. So any factor of 90 that is not a factor of 30 is out. So 18 is out, 45 is out, 90 is out, plus or minus. 9 is not a factor of 30. So I have now eliminated those. I could look at the others farther, but I am going to, well, I suppose I can get the 9 halves out of here and 9 fourths, but I think the rest of them Well, these, not the negatives. So I've now narrowed it down again, but I'm also making my synthetic division easier now because I am no longer using the original polynomial. Now I'm looking for factors of that, the cubic. So now I start with 4, 12, -7, and -30, and I'm going to do synthetic division here. And I need to test 3. I need to check in case of multiplicity. I'm going to test this because it's possible to have a root of multiplicity greater than 1. So 4, 3 times 4 is 12, plus 12 is 24. 3 times 24 is 60, 72, plus -7 is really big. And then it's going to be also positive. So now I see an upper bound. And I can go back up and cross off any root that is greater than +3. So that means +5 is out, +6 is out. Those I've already done. +15 halves is out, and 15/4 is greater than 3. So I'm slowly narrowing down my list. Let's try 1. So bring down the 4. 1 times 4 is 4, plus 12 is 16. 1 times 16 is 16, plus -7 is 9. 1 times 9 is 9, plus -30 is -21. And what I see here, again, going from a positive function value to a negative function value, I know there's going to be a root between because of the intermediate value theorem. So we already saw that 2 was not a root, so now I have to try a fraction. Let's try 3/2. So I bring down 4. Half of 4 is 2 times 3 is 6. 6 plus 12 is 18. Half of 18 is 9. 9 times 3 is 27. 27 plus -7 is 20. Half of 20 is 10. 10 times 3 is 30. 30 plus -30 is 0. And I found another root. And so now I'm going to factor again. So this tells me x minus 3/2 is a factor. Those are factors. So I'm going to factor x minus 3 from the previous synthetic division, x minus 3/2, and now I'm left with 4x squared plus 18x plus 20. And once I get down to a polynomial, or sorry, once I get down to a quadratic, I can attempt to factor this or use quadratic formula. Now, one thing that kids try to do is they go, oh, well, x minus 3/2 is a factor. Since 3/2 is a root, then that means 3x minus 2 is also a factor, which is true, but then they go 4x squared plus 18x plus 20. That is not an equivalent polynomial because the purple polynomial has a leading coefficient of 4, and the blue polynomial has a leading coefficient of 3 times 4. Those are not the same polynomial. So don't do this. I take off too many points. If you are going to multiply, if you're going to, oh, I wrote that backwards. This is 2 minus 3. So this would have a leading coefficient of 8. I did the converting backwards. The way to keep that a polynomial, you could say f of x equals x minus 3 times 2x minus 3. But I now multiplied both of those terms by 2. So I'm going to need to divide the other terms by 2 here to keep it balanced. Because if I multiply one factor by 2, I have to divide another factor by 2. Otherwise, I see a change in the leading coefficient. And if I look at this polynomial, my leading coefficient is still 4 because I have 2 times 2. So then if I were, let's see, 2 numbers that multiply to make 20 and add to make 9, I believe that's 4 and 5, so f of x should factor to, if I factor this one, I need positive 4 and positive 5. So that's going to give me 4x, and 5x gives me 9x. So now my zeros, or my roots of my polynomial, are at 3 3/2, -5/2, and -2. And what you see is all of those were in that original list.